So let's go ahead and talk about limits. Well, actually, we'll start with problem. This problem 14 from section 9.1, which is the domain function, domain question. Write down some things. Co-17C. Today is January 10th. And the first question is to find the domain of the function f of x comma y equal to the square root of x times y, right? Yeah. So, is that the one you wanted? Okay. So again, whenever we're finding domain of a function of either one or two variables, we're almost, and again, it's not one of those ones where like you have to think about the context of the question where like the x's and y's represent like the number of people or something, right? Not the case here. X and y can be anything that's valid. So we're going to start saying, well, I have a square root. I don't have any quotients. I don't have any logarithms, but I definitely need for the inside of the root to be non-negative. So this is actually a little bit interesting, I think. I don't feel like there's really a good way to do this other than just kind of to think about what we can have. So certainly one option is that x and y are both positive. Another option is that x and y are both negative. A third option, so I will point out that currently that would give us all of the first quadrant, not including the axes, and all of the third quadrant, not including the axes. But we're not quite done because it would also be valid to include the entire x equal to 0 and y could be anything. Right? Because 0 times a negative or a positive number is still going to be 0, and the square root of 0 is still valid. And similarly, y equals 0 and x can be anything. So x equal to 0 is the y-axis, so we do get the entire y-axis, and y equal to 0 is the entire x-axis. So there's our entire domain. The axes included, as well as all of quadrant 1 and all of quadrant 3. A little funky, but not too terrible. If, on the other hand, if the question had been, what's the domain of g of x comma y equal to the natural log of x times y, then we would not include the axes, because here our domain would be the solution to the inequality, excuse me, x times y is strictly greater than 0, and then we would, so drawing this would be kind of a giant pain, I think. So we don't want to include the axes, and normally you would just draw them like axes, right, like regular lines, but here we would probably actually draw the axes as dashed lines. So I'm going to draw my x-axis and my y-axis as dashed. There's my y-axis, there's my x-axis. I should label it here to make sure everyone knows what's going on. So here's my x-axis that I'm not including. Here's my y-axis that I'm not including. And then I want still the same, all the points in the first quadrant, all the points in the third quadrant. So that's how that would differ from the other one. Those of you just joining us, here's the attendance form. Please do fill it out when you have a moment. This is the graph of the domain of this function. So the only difference here is that for this domain, the axes are included, right? For example, the point 3 comma 0 or 0 comma 5 or 0 comma negative 4, all those are points that are in the domain of this function, because if you plug those in, 3 times 0 is 0 and the square root of 0 is valid. Or 0 times negative 4 is 0 and the square root of 0 is valid, right? Any point on these axes is going to give you a product that's equal to 0, and we can take the square root of 0. On the other hand, with this extra problem here, any of those points would no longer be valid because the product of 0 and something else is 0, and the natural log of 0 is not something that's defined. So, not be valid. Other domain questions before we start talking about this. Yeah.
It's 21.
21.
Or actually, 19, sorry.
Sure. Sure. I think we'll do 18 and 19 because I think they're both kind of interesting. Let's look at 19 first. So 19, the function is given by, sorry, not f of x. Oh, you can't even see that. Cool. You can't see it, so it's not there. So the function is given by f of, I think it's x, y, z. Yeah. X comma y comma z is equal to the square root of 1 minus x squared minus y squared minus z squared. Yes, it is. I will point out here that our domain is going to be a set of points in three-dimensional space because our function is a function of x, y, and z. So if your function is a function of just x, your domain is something in the real number line. If your function is a function of x and y, your domain consists of points in the xy plane. And if your function happens to be a function of x, y, and z, your domain consists of points in three-dimensional space. So here, it's still the same as everything else, right? It's always the same thought process. Do I have a quotient? No. Do I have a logarithm? No. Do I have an even root? Yes. Okay, great. The stuff inside the even root has to be greater than or equal to 0. So I would say generally with these kind of problems, if you ever see an x squared plus y squared or a negative x squared minus y squared, you should isolate that. And the three-dimensional analog there is if you see an x squared plus y squared plus z squared or a negative x squared minus y squared minus z squared, you should isolate that, but you make it positive. So I would bring all the variables over to the other side of this and rewrite it as, I want to write it on the left. I don't want to write 1 is bigger than or equal to x squared plus y squared plus z squared. I really would prefer to write x squared plus y squared plus z squared is less than or equal to 1. That's how I want to write it. And then to deal with an inequality, we usually think about the equality. So I want to think about what is the graph of x squared plus y squared plus z squared equal to 1. Any suggestions, thoughts, guesses? What does that surface look like? Yeah, it's, what do we call it? A sphere. Yeah, a sphere, right? So just to point out, a sphere is just like a circle. The sphere is just the exterior, right? The circle is all the points that are on the circle. It's not the stuff inside. If you want the inside points, we would call that the disk. Three-dimensionally, if you want the inside points of a sphere, you call that a ball. Which I don't think is a good description because if you think about most balls, they're usually filled with air, so they feel kind of like they're empty. But that's what it's called in math. You call it the ball. So this is a sphere of radius 1. So the question is, do we want all the points inside or outside? Well, I'm going to pick a test. So here, I'm not as good at drawing in 3 dimensions, so I'm just going to imagine. Well, I know inside the sphere of radius 1, certainly the origin is in there. It's the center. So I'm going to test to see, okay, great. Is the origin in the domain? In other words, does the point 0, 0, 0 satisfy the inequality? X squared plus y squared plus z squared less than or equal to 1. And it clearly does. 0 squared plus 0 squared plus 0 squared is 0, which is less than or equal to 1. Yes. Which means that point, which is inside the sphere, is included, and that means all the points inside the sphere are what our domain is, including the boundary, right? Because it's less than or equal to 1. So our domain here is all points inside and on the sphere of radius 1, centered to the origin. I don't think drawing it's super useful here because I'm just going to draw a thing and be like, yeah, all the points inside. So here's my drawing, but I don't think it's particularly great. I don't really want to like shade that in because it's just going to make it look worse, I feel like. So it's all the points inside there. I could try yeah, it's everything inside there. Did that make it look better? No. There's my domain that they asked me to graph. Because that's what the problem says, right? The problem says Find and sketch the domain. I guess technically I didn't write the domain. I wrote words, but if I was going to write it, I would write domain as a set of all points x comma y comma z such that x squared plus y squared plus z squared is less than or equal to 1. That's how we would actually write the domain, even though I feel like it doesn't tell us anything extra. Let's look at problem 18 as well, because I think it's a little more interesting. Yes, I can. I will also point out, while you're certainly welcome to take pictures of anything, I do post the notes, which on campus, so you certainly can access them really easily as well. So welcome to take pictures, also welcome to find them on campus or on the Google Drive, which is where they're actually posted. Okay, so problem 18 here was, yeah, I think this is kind of interesting. F of x comma y. I'm going to change up a little bit. I don't need to be exactly problem 18. I want to make it a little bit different. Is equal to the square root of x plus y. Yeah, I like that. Plus, let's say the natural log, that'll be more interesting, of 25 minus x squared minus y squared. Cool. Oh, sorry, you can't see that. Apologies. Well, hi there. So looking at this, you should see one thing immediately. You should be able to look at this and know that the circle of radius 5 is in play. Right? That's just gonna happen, right? That 25 minus x squared minus y squared. Right, okay, there's gonna be some sort of circle of radius 5. I should have made it different, but well, that's fine. So here I have two things I have to account for. I have to account for this square root here. So that's going to tell me that x plus y has to be greater than or equal to 0. Well, I was trying to number things. And you guys might know it like never really happens for very long. But this is number 2 over here. Problem number 3 that we're looking at over here. So we need this. And usually if you've got something like this and you're trying to graph it, if you can isolate y, it typically makes sense too, because we know usually how to graph y as a function of x is a more typical way of graphing things. So I'm gonna say, great, y is bigger than or equal to negative x. We'll graph that in a moment. Over here, we have 25 minus x squared minus y squared is greater than 0. So we have x squared plus y squared less than 25. It's not necessary to write your variables on the left. It just feels like it's the right way to do it. So what I'm really thinking about doing is bringing the x squared plus y squared over to the right, writing 25 bigger than x squared plus y squared, and then rewriting my inequality so x squared plus y squared is less than 25. Or you could do this where you're like negative x squared minus y squared is bigger than negative 25, and then multiply everything by negative 1 to do that. I don't like multiplying inequalities by negatives unless I have to. So I've got both of these things going on here. So y bigger than or equal to negative x. I'm just going to graph y equal to negative x. Graph y equal to negative x. And I'm going to graph it solid because I know it's going to get included because where there's a greater than or equal to there. So we know that we're going to include the boundary, whichever side of it we happen to have. So here's my y equal to negative x. Great. And then I'm also going to graph x squared plus y squared equal to 25. But this one I graphed solid. This one I'm going to graph dashed because I don't want to include the boundary there. I don't want to include x squared plus y squared equal to 25. I want just one side of that boundary. So let's say that's 5, that's 5, that's 5, that's 5. And there's my boundary being all dashed. So you essentially have 4 different places you could end up. It could be everything out here. It could be everything in here. It could be everything in here, or it could be everything out here. So let's try to be sensible about this. I would love to just pick the one that it actually is instead of having to try and test points of all the ones it's not. So if I want y to be bigger than or equal to negative x, typically if y is bigger than something else, that usually means you're vertically above that line. So I'm pretty confident I'm not down here. I'm pretty confident I'm up here somewhere, I think. We'll test the point in a second. Also, if we're x squared plus y squared less than 25, that usually means you're inside the circle. If it was bigger than 25, it would mean we were outside of the circle. So I'm pretty sure I'm in here. Let's test the point. Let's test the point 1, comma 0 and see if it works. So if x is 1 and y is 0, well, it certainly checks out here. 1 squared plus 0 squared is less than 25. Check. Let's check over here. If x is 1 and y is 0 bigger than or equal to -1? Yep, that checks out as well. So it looks like there's my domain. All the points inside this half of the circle, including the points on this line, but not the points on the end of the circle there. Kind of cool. All right. You have to keep track of these notes, especially here, because there's stuff on the back. So let's talk a bit about limits. What I would say about limits is, well, yeah, much like in 17A, we found limits sometimes by finding like two-sided limits and seeing if it existed or not. The same kind of idea is going to be true here. So, for example, we'll go back to 17A for a second. The 17A example. If your piecewise function was equal to, say, 2 minus x when x is less than or equal to 1, and x squared plus 1 when x is bigger than 1. Yeah. Because it was in the section that I was pretty confident was the domain. But so I'll say a little bit more here. I'm definitely trying to pick a point that is not on one of the boundaries, right? I wouldn't want to pick something that's on the circle or on this line. So I picked something that was a little to the right. I know that this point over here is 5, comma 0. This point up here is 0, comma 5. I could have tested points in all 4 bounded regions, though, or I should say all 4 distinct regions. So like if I pick a point out here, go big, so you know it's not included. So I pick the point, I don't know, like 8, comma 5, sure, 8, comma 6. It's clearly not going to meet this criteria, right? 8 squared plus 6 squared is definitely bigger than 25. Similarly, if I pick something over here, like -1, -1, it's going to meet this criteria, right? -1 squared plus -1 squared is less than 25, but it's not going to meet that criteria because -1 definitely is not bigger than or equal to -1. -1 is not bigger than or equal to +1. Finally, if I pick something out here, let's go way over here, like the point -8, comma 0. Well, again, not going to meet this criteria because x is 0 and x is -8 and y is 0. So 0 certainly isn't bigger than or equal to 8. And I can also check over here. It also wouldn't meet that. But once you failed one of them, you don't have to check anything else, really.
Squared plus y squared, we know that's going to be inside because of the residence.
Mm-hmm.
So with the other equation, since both variables are opposite ends, can you not tell?
It can be harder to tell, yeah. So typically, not always, but typically, if you've isolated y and you have like y bigger than or equal to some function of x that is like a nice curve we are able to graph, that usually means we are physically above the curve. So like if I was graphing something like, or trying to find a domain that was like y bigger than or equal to x plus 1 squared, for example, I would graph y equal to x plus 1 squared, which is your usual parabola shifted 1 to the left. And then I would be fairly confident that it's everything up here above, not everything down here below. I would still check, right? I would check the point like 0, comma 7 and be like, oh, x is 0, y is 7. Yeah, that checks out. That satisfies the inequality. So that means that everything on this side of the graph is included in the domain. But yeah, so usually if it's a y bigger than or equal to it's everything above, it's a y less than, it's everything below. If you're just isolating y. Okay, so looking at this function, if I want to talk about the limit as x approaches 1, I would look at the limit from the left and the limit from the right because the function changes from one piece to another. And here we would see that the limit as x approaches 1 from the left, we're going to use the piece of the function when x is less than 1. So that's going to be the limit as x approaches 1 from the left of 2 minus x. Most of the time, if we can just substitute in the value x is approaching, we do. Here we get 2 minus 1, which is 1. That's the left-hand limit of this function. On the other side, the limit as x approaches 1 from the right of f of x, we get the limit as x approaches 1 from the right. We use a piece of the function where x is bigger than 1, which is x squared plus 1. We again substitute 1 in for x, and we get 1 squared plus 1, which is 2. Those aren't the same, right? The limit from the left and the limit from the right aren't matching up, so the limit doesn't exist. So we say, great, or not. The limit as x approaches 1 of f of x does not exist because the limit from the left and the limit from the right don't have the same value. We can also see this graphically. Right? If we graph this thing, it looks somewhat like this. Let's see. Sure. Looks like that from the left. And then from the right, it looks like kind of like that. And you can see, right, here's the point 1, comma 1. Here's the point 1, comma 2. Yeah, the right-hand limit, left-hand limit definitely aren't matching up. That idea holds, meaning that for functions of two variables, we're typically going to show that the limit doesn't exist by showing that instead of the left-hand limit and the right-hand limit not matching up, limits that approach a point from any direction all have to match values for the limit to exist. And if the limits don't match on any path, then we see the limit doesn't exist. So let's look at some examples. So we'll look at the limit as x comma y approaches 0 comma 0 of 2x squared y over 3x squared plus 4y squared. Oh, wait a minute here. Ooh, this is not the example I want to start with. So the other problem with not being able, I wasn't able to print out my notes was that the notes I usually refer to. Let me grab my notes real quick here because there are definitely examples I have in mind that I want to make sure I hit. And I thought I was looking at the right one, but I definitely am not. We will see about the last one there. 1 second here. Sorry. Apologies. It's no fun when your printers don't work. Let's see where we at here. We'll come back to that example. Yeah, there we go. Cool. Yeah, let's start with an easy example. So just like with functions of one variable, functions of two variables have limits that work kind of nicely sometimes. So for example, limit as xy approaches 1 comma 2 of x squared plus y cubed minus 3. We got no problems here, right? We can just plug in 1 for x and 2 for y and see whatever value we get. In this case, it's going to be 1 squared plus 2 cubed minus 3, which is 1 plus 8 minus 3, which is 6. And that's it, right? Just like with 17a, if you can plug in the values that x, or in this case, x and y are approaching, and get a real response, you're good to go. Of course, it's not always going to be that easy, right? Why would we make it easy? So it gets harder. Often, just like with 17a, we're going to be dealing with limits of a 0 over 0 nature, which not always involve, oh, sorry, I didn't mean to, sorry, I'm not approaching 0, 0 here, I'm approaching 8, 8. Sorry about that. The limit as xy approaches 8, 8 of x squared minus y squared over x plus y. Yeah, sure. I already made my bed. I'll lie in it. All right, so, oh, that's terrible, actually. That's fine. It's still a valid question. It's not what I meant to do, but still good. If we plug in 8 and 8, what happens? I get 8 squared minus 8 squared over 8 plus 8. which is 64 minus 64. So 0 over 16, and 0 divided by 16 is 0. Check. That's the limit. Now we'll change it up. Do the limit as x, y approaches 8 of x squared minus y squared over x minus y. And in this case, if we plug in 8 for x and 8 for y, we're going to get 0 divided by 0. Which, as I've seen in the past, means you have to do more work. It could be anything, right? It's literally an indeterminate form, which means it could be any value. In this class, 17C, most of the time that means it's going to not exist. Not always, though. There are plenty of 0 over 0 elliptic limits that do exist. Sometimes, like in this example, you can do some factoring and canceling. Check it out. If we factor the numerator as x minus y times x plus y over x minus y, we can cancel the x minus y's and get the limit as x comma y approaches 8 comma 8 of x plus y, which is 16. And that's the limit here. This function isn't defined at the point 8 comma 8, or actually at any point along the line y equals x. In fact, graphing things. I always think it's kind of nice to see these things. So taking a look over here for just, whoops, come on. So if we graph this, z equal to x squared minus y squared, yeah. Divided by x minus y. That looks super funky. So if you look at it, it kind of just looks, in fact, not surprisingly, it looks a lot like if you graphed z equal to x plus y. In fact, it's literally the same, except when x and y are equal to each other. So I know it's kind of hard to see because, right, of course it's hard to see. But if you look at the surface here, we're missing all those points on that line right there. In fact, let's be smart, James. Let's graph y equal to x. So all those points where the green plane and the red plane intersect each other, those points aren't points that are actually on the graph, right? The graph is undefined there. However, we can see that no matter, like, if you look at the point, sure. You look at the point, let's pick an easier one. Sure. 8 comma 8 comma 16, which maybe will show up on my graph if I'm zoomed out enough. I have no idea how far zoomed in I am. I can't even tell. Am I zooming in or zooming out? Who knows? It's really impossible to know. Sorry, I know it feels real silly. Let's you can do this to reset where you're at. But again, it just looks the same. Let's go small. So instead of 8, 8, 16, let's pick like 1, 1, 2. So you can see, hopefully, kind of right there, there's that point. So the limit as xy approaches 1, 1 would be 2, even though that point isn't actually on the surface. Because again, if you actually plugged in 1 for x and 1 for y, sorry, you can't see the thing I'm pointing to, apologies. If you actually plugged in 1 for x and 1 for y, you would get 0 divided by 0. But just like in 17a, the function doesn't have to be defined somewhere for the limit to exist there, right? You just have to have left-hand value and the right-hand value coming closer to each other. Or in this case, the values from every possible direction of approach towards that point all being the same. And they are in this example. Cool. So let me grab that again. Where'd you go? Sorry, I want you back. No, I don't want you back. Go away. You come back. Sorry, it's always my cursor is always a million, super hard to find. There we go. Cool. That said, a lot of the time, these indeterminate limits are not going to exist. So for example, keep going to the side here, we might look at something that looks very similar, but is not the same. The limit is x comma y approaches 0 comma 0 of x squared minus y squared over x squared plus y squared. In this case, if we plug in 0 over 0, we're still going to get indeterminate, right? It's going to be 0 divided by 0. And unfortunately, although you could factor the top, factoring the top isn't going to lead us anywhere. It's not going to, nothing's going to canceling. So typically here is where we employ the method of picking different paths that go through the point that x comma y is approaching. And there's some pretty standard choices, but let me list a few of them. So specifically, if you're trying to go through the point 0, 0, there's a set of paths that we start using, and the hope is that eventually two different paths will produce two different limit values, which then allows us to conclude that the limit doesn't exist because you get two different values. So some common paths are straight lines that go through the origin. So I could say something like y equals x, or y equals 2x, or y equals any multiple of x. You know what often gets overlooked, which are kind of the best choices to do first? Y equals 0 and x equals 0. These should be your bread and butter path choice. Like these are the first things you should try every time. Often they will give the same result, but it's good to do at least one of them. So I would say these are first and foremost, right? Y equals 0 and x equals 0 are the paths you want to choose first. Then you might try y equals x or y equals 2x. And then so here's the thing, you keep trying things until either you've convinced yourself that the limit does exist, and then you have to do other work that's terrible, or you get to a place where something's different. So if you've tried a bunch of these and you're still getting the same limit every time, like 3 or 5 or whatever, then you start trying other paths, like maybe y equals x squared, which goes to the origin like that, or x equals y squared, which goes to the origin like that. Any curve you can think of that goes through the origin, if you're approaching 0, 0, is a valid choice. You can even pick y equals sine of x, or x equals sine of y, or other weird things. I usually don't pick those. Standard choices are powers of x, powers of y. So you could do y equals x cubed, x equals y cubed, and then really y equals x to any power, x equals y to any power. You do not want to pick roots generally, because like the square root of x or the cube root of x, I don't want to do y equals the cube root of x. I want to do x equal to y cubed. I don't want to do y equal to the square root of x. I want to do x equal to y squared, because that, right, x equal to y squared is all of this, where y equal to the square root of x is only one side of that, which is limiting. So it's usually not a good choice to pick a root. Those are pretty much the standard choices. So here, I always start off with the easiest things first. So if I try, say, y equals 0, so here's what you do. When you set y equal to 0, you literally rewrite it with y equal to 0. So I'm going to say, well, y is already 0. It's no longer approaching 0. Y is 0. So I'm going to rewrite this as the limit as x approaches 0. And it's going to be x squared minus 0 over x squared plus 0. So now the limit as x approaches 0 of x squared over x squared, well, x squared divided by x squared is always 1 as long as x isn't 0. And I'll remind you, when you're finding a limit, we're saying what happens is x gets really, really, really close to 0 but isn't equal to 0. So as long as x isn't 0, x squared divided by x squared is 1. And this value is always 1 except for when we get right at 0. But again, that's not something we have to consider. This is equal to the limit as x approaches 0 of 1, and the limit of a constant is that constant. Cool. That check mark is dumb. I did the limit. That doesn't mean that's what the limit is. This means I've done with that step. Because now I have to check a different path and hope that they get a different value. I would probably try x equal to 0, although I will say again, a lot of the time, y equals 0 and x equals 0 give you the same result. They're not going to here, but a lot of times they do. So we try x equal to 0. we're going to have the limit as y approaches 0 of 0 minus y squared over 0 plus y squared. Simplifying this, negative y squared divided by y squared is equal to -1. So it's the limit as y approaches 0 of -1, which is -1. Those two values are not the same, so we can conclude that the limit as x comma y approaches 0 comma 0 of x squared minus y squared over x squared plus y squared does not exist. If you wanted to write more words, you could. The words I write is because two different paths produce two different limit values. So that's kind of the typical gist for these limits is you're trying to see if you can find different paths that give you different values. If your limit is not going through 0, 0, it's usually much more complicated because it's harder to find paths that go through other points, right? 0, 0 is an easy point on the xy plane to find a function that goes to that point. Other graphs are more, or other points are more challenging, but not impossible. Let's look at some more examples. Yeah, we got. I will say, your teacher like briefly mentioned continuity. Functions are continuous, basically. Well, like in 17a, they're continuous if the function exists at a point, the limit exists at the point, and they're equal to each other. So here it really kind of boils down to making sure the limit exists and is equal to the function value. So I don't imagine you'll be asked a lot about continuity. Like I don't even know if there were any homework problems about continuity. Nope, I don't see any that were assigned. With good reason. They're not, it's not really the gist of the class. Like it's an important concept, but it's not really what we're going here. So let's look at another example. Let's look at the limit as x comma y approaches 0 comma 0 of 6xy over x squared plus y squared. You should at least mentally check. You don't necessarily have to write it down. We should check inside your head. If I plug in 0 for x and 0 for y, do I get a real number or do I get something that's indeterminate? Here we get 0 divided by 0 if we plug in the 0, so we can move on to checking different paths. So let's pick some paths. And again, apologies for the notes on. Yeah, I guess you can't really see that. You can kind of see there's like some writing on the backside of that page, but it's faint enough, I think, that it's not the worst thing I've ever done. So again, let's try the usual path. Let's try y equal to 0. Should always try at least one of those paths. So if we do that, we're going to get the limit as x approaches 0 of 6 times x times 0 over x squared plus 0 squared. You can skip this step, right? You should know that 6 times x times 0 is 0. And x squared plus 0 squared is just x squared. I would not skip this step, but I would write that first. And then be like, oh, 0 divided by not 0, right? X squared is specifically not equal to 0 if x is approaching but not equal to 0. So we can really think of this as, oh, that's the limit as x approaches 0 of 0 divided by not 0 is 0. And the limit of a constant is whatever that constant happens to be. Okay. I don't want to write it down, but I will point out that if we checked y equal to 0, we get the same result. Sorry, x equal to 0. We definitely check the same result if we set y equal to 0. If we set x equal to 0, we're also going to get 0 divided by y squared, which will just be 0, who's going to be 0. So we need to pick a different path. Let's try, sure. So I usually kind of go increasing in power, so I'm going to try y equals x. And in this case, you can kind of write it either way you want. You can either replace the y's with x's or the x's with y's. I and you all probably have a general tendency to prefer to write things in terms of x instead of in terms of y. Just feels more typical. So if we replace the y's with x's, we're going to get the limit as x approaches 0 of 6 times x times x over x squared plus x squared. Simplifying this, you get the limit as x approaches 0 of 6x squared over 2x squared, which is the limit as x approaches 0 of 6 divided by 2, which is 3. And once again, the limit of a constant is just that constant. And since those two limits along different paths have different values, the overall limit does not exist. Okay. Questions before we do one more example like this? Yeah, we got time. We got time. It's not real. So let's look at this next one. It's a little bit more challenging. Once again, the zero, though. The limit as x comma y approaches 0 comma 0 of 8x squared y over x to the fourth plus 3y squared. All right, I want all of you to try either x equal to 0 or y equal to 0 on your own, real quick. Good. So I'm seeing along the path x equal to 0, the limit ends up being 0. That'll happen a lot because often if you're going along x equals 0 or y equals 0, the entire numerator will frequently end up being just 0 and the denominator will end up being something that is not necessarily 0, and so then it equals 0. And if any of you tried the path y equals 0, you probably got the same result. Not probably, you definitely should have gotten the same result. So, okay, let's start looking at other paths. And this is where things get a little bit kind of like, how long do you do this until you're like, well, maybe the limit exists? I don't know. It's kind of hard to know. Your teacher didn't talk about any limits existing, right? Any 0 over 0 types of limits existing. So my bet, I won't see that, but we should still do one. Probably not today though, because it's a little involved. So actually, I should look at one more thing here. Yeah, it's hard to tell looking at these examples if any of those limits he was assigned to you actually exist or not. Again, since the homework's not due, let's look at this one. Oh, sorry, I have to pick another path. Apologies. So another path, let's try y equal to x. A good path to pick. So we're going to get the limit as x approaches 0 of 8 times x squared times x over x to the fourth plus 3 times x squared. When you have something like this, where the powers don't match, you typically, right, if we plug in 0, 0 right now, we're going to get 0 divided by 0. But it doesn't mean it's indeterminate. It means you have to do some work. Here, in the denominator, I can factor out an x squared. So I can rewrite this as the limit as x approaches 0 of 8x cubed divided by x squared times x squared plus 3. I can cancel the x squared and get the limit as x approaches 0 of 8x divided by x squared plus 3. I can then plug in the 0 and get 0 divided by 0 plus 3, which is 0. Which doesn't help me because it doesn't tell me the limit doesn't exist. It also doesn't tell me the limit does exist, right? Because to show the limit exists, you can't just keep trying paths. You actually have to definitively show it exists through another method, which I know again, we haven't talked about. But I've only tried 2 paths, so I should not just give up yet, right? There's other paths to try. Here is the usual kind of, what's the word I'm looking for here? Guidance, thought process, what you're trying to achieve. You would really, really like to pick a path where all the terms in the numerator and all the terms in the denominator happen to have the same power of either x or y. We would love for that to happen. It would be ideal. And here, that'll happen if we pick the path y equal to x squared. So if we pick the path y equal to x squared, look what happens. We get the limit as x approaches 0 of 8x squared times x squared over x to the 4th plus 3 times x squared squared. If we simplify that, we get the limit as x approaches 0 of 8x to the 4th over x to the 4th plus 3x to the 4th, which is 4x to the 4th. The x to the 4ths cancel, and you're getting the limit as x approaches 0 of 8 over 4, which is 2, and the limit of a constant is the constant. And then, since this is 0 and this is 2, it means the overall limit does not exist. So it's not always easy to come up with exactly the right path that's going to make this kind of thing happen. And this kind of thing doesn't always happen. But a lot of examples that teachers come up with do have this kind of thing happening. So it's a good thing to look for. What can you choose y to be equal to or x to be equal to that goes to the point of 0, 0 is going to make this kind of thing happen. I would point out, I'm not going to do it, but I'll point out, here's a similar example. If I did like, say, the limit as x comma y approaches 0 comma 0 of 8y cubed x over y to the 6th plus 2x squared. Yeah, that'll work. There is definitely a path through the origin that achieves the same sort of result, where you'll get the same powers in every term. And I believe it's x equal to y cubed. You should try it on your own. How much time? Not really enough time. So I had one more example I wanted to mention. I know I've got like less than a minute here. I'm gonna write it down anyway. So here's the last example I wanted to point out, which is not approaching 0, 0. It's the limit as xy approaches -1, 1 of x plus y over xy plus 1. And I'll point out that this too, almost all these questions are going to be indeterminate, right? It's not really interesting if it's not. So if you plug in -1 for x and 1 for y, you're going to get 0 divided by 0. Here, it's much more difficult to come up with paths that go through the point -1, 1. I can think of 3 off the top of my head. 2 easy ones. Y equals 1. X equals -1. And then I could think like y equals -x. I suppose y equals x squared would also be good. It goes to that point too. So there are paths to come up with. They're just not quite as easy to discern. If we try the first two, we try y equal to 1. We're going to get the limit as x approaches -1 of x plus 1 over x plus 1. That's nice. What's that going to be? Everybody should be able to tell me what that's going to be. What's x plus 1 divided by x plus 1? So the limit of 1 is 1. Right? We can cancel those. X plus 1 divided by x plus 1 is just 1. If on the other hand, x equals -1, then we have the limit as y approaches 1 of -1 plus y over -y plus 1. And if we look at that, you might notice that those things are essentially the same except opposites. So if you factor out a -1 from the bottom, we can rewrite this as the limit as y approaches 1 of y minus 1 over -1 times y minus 1. The y minus 1's cancel. Left the limit as y approaches 1 of 1 over -1, which is -1. And oh, they're not the same. So the limit doesn't exist. this limit is x comma y approaches 1, sorry, -1 comma 1 of x plus y over xy plus 1 does not exist. On Monday, we'll talk about at least one example where it's a zero limit and limit does exist and how you would show that's true. But I don't think you need to worry too much about that because, well, I think you don't need to worry about that, but I'm not 100% sure because you never know, right? People assign things and they're like, oh yeah, that's no problem. So I'll show you an example. We can talk more about it. You might ask your instructor if he expects you to be able to show an indeterminate limit exists. It might be worth it to know whether or not you have to be able to do that, but yeah, that's all I'll say. Have a nice weekend. I'll see you all on Monday.